So we're wanting to predict if a reaction is spontaneous, if a process is spontaneous. And I told you in our last lesson that we have to define another thermodynamic term here, and this is entropy. We have to look at entropy and define what it is and get a feel for what entropy is a measure of. So here's the definition. It is not a straightforward, easy definition to hold on to, but we're going to define it. We're going to look at these words. So it's a thermodynamic function. It increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. That seems very convoluted. So I'm going to try to give you a feel for what those words mean, and then I'm going to give you a way of thinking about it that's a lot easier for our brains to wrap around. This is the true definition. We need to understand this true definition, and then I'll give you kind of a, like I said, a mental way to wrap our brains around this. So let's start with the image that we see on the screen here. I'm going to move over and kind of talk about it over here. I've got two different systems, okay? So we have system A and system B. In system A, I have little objects, and if they are on this line, they have 2 joules of energy each. So what would be the total energy in this system A? Well, it would be 4 joules, okay? Now, that is all we have. That's the only option we have. Now we have system B. In system B, there's 2 different places. 1, 2. There's 2 different places that the balls can be. They could either be at this level here, which has an energy of 1, or it could be at this level 2, which has an energy of 3. Now, the way the system is right now, we've got the red in this one up high, number 2. We got the blue in the one at energy 1. And what is the total energy? Well, it is also 4 joules, okay? So, are they energy equivalent? Well, yes, but these are 2 different systems. Now we're going to consider the number of energetically equivalent ways to arrange it. If you look at system B here, okay? System A, you can only have what you have, but in system B, are there more ways that you could arrange those in order to come up with 4 joules? Think about that. What if instead of the blue being down here, it was up there, and instead of the red being up here, it was down there? Would that be a different arrangement? Certainly. But would it be the same? Would it be an equivalent, energetically equivalent way of arranging them? Yes. So in system B, we have 2 ways that we can put those objects to give us 4 joules. So we would say that this system has a greater entropy because it has more energy equivalent ways of arranging it. So when you can divide out where those things can be more, you're going to get a greater entropy in your system. Now that's one way to look at it, and I want to give you another way to look at it. Oh, before I do that, let's define what a microstate is. A microstate is abbreviated with a capital W, so it doesn't get confused with work, which is a lowercase w. And the number of microstates are the number of, it's all of that information that is underlined there in blue, the number of energetically equivalent ways to arrange the components of the system to achieve a particular state. So however many of those you have would be your microstates. So in this system, there is only one microstate. In this system, we could have the objects like I see them in the picture or flip them, and so this would have 2 microstates, and it has more energy equivalent, blah, 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 keep wording, or we can just say it has more microstates. Now, how does microstates and entropy compare? It's with this equation. Now, you will never have to mathematically use this equation in this course, but you need to see that as the number of energetically equivalent energy states occur, the greater the entropy. And this is truly how we define entropy. How is it calculated? How is it defined? As W increases, S is going to increase. If there was only one possible energy equivalent microstate, then the entropy would, well, the natural log of 1 is 0. You would have a 0 value for your entropy. Now we're going to look at it a different way. We're going to draw some boxes, and I'll go back to my screen for this, and then I'll let you kind of finish it out once I get you started. I have 2 boxes. So over here I'm going to draw 2 boxes. Okay? In one box I've got 4 objects. Okay? So I'm going to draw my 4 objects. See if I can keep all these colors straight. Oh, I probably should put my pink over here. I think I can do that. I'm going to put my pink over here, and I'm going to put, because these are going to show up on your screen as looking very, very similar, I'm going to put my green over here. So you're going to have to take my word that this is yellow. I know. I can put a Y in it for yellow. Nope, that doesn't help either. Okay, so I have yellow, I have green, I have 4 objects, and I have 2 boxes, and I want to think about all the different ways that I can do that. Well, one way I could do this, okay, and here is my 2 boxes, is I could put 3 of them here and let 1 of them go over to the other side. So I'm going to see if I can take all my little pins here and keep track of everything. So the first one I want to move over is the green one. I mean, it's the blue one. So I've got my green, my yellow, and my pink, and I'll keep them kind of in their location. So that is 3 in the left box, 1 in the right box. Well, can I come up with an equivalent way that is equivalent but different? Well, what if I leave the blue one here, and the green one here, and the pink one here, but I move the yellow one over? Okay, so I'll move the yellow one over. These would be equivalent. They both have 3 and 1 on the left and 1 in the right. They're equivalent, but they're different. Okay, so let's draw another one. I could have, this time, maybe I will move the green one over. Okay, so I have my blue, my yellow, my pink, and I'll choose to put the green one over here. Now I have 3 equivalent but different. These were microstates, okay? Could I do another one? I'm going to tell you I could do another one. Look at it. Pause it if you need to. What would be another one that I could draw? Well, which one have I not yet moved over? The pink guy hasn't gone over yet, so let's put the pink one over here, okay? So the blue, the yellow, and the green. So this one has 4 equivalent microstates. 4 ways of arranging them that are equivalent. How are they equivalent? They have 3 on one side and 1 on the other. That's equivalent in every one of these boxes. But it's a different 3 here and a different 1 there. Now I want you to stop and try another set, okay? I want to get you started. In this case, I moved 1 over. What if I moved 2 over instead? Okay? Give yourself some boxes and think about how many equivalent, meaning there's 2 in one box and 2 in another box. They're equivalent, but they're different. And then I want to see if you can just ponder all the possibilities of 4 particles in 2 boxes. Pause it, and then we'll resume. Okay, so hopefully you worked through that and you took the time to do it. I took the time to do it by copying and pasting this image into my slideshow here. And let's look at all of those different microstates while I put all the lids back on these poor little pins so they don't dry out. Okay, so the one with 2 balls, 2 particles on the left and 2 particles on the right stands out to me in that it has the most equivalent microstates. So if we were going to look at those guys on the PowerPoint slide there, we could ask ourselves which one has the most entropy. Well, it would be the state that has the most equivalent microstates. So that would be this one right here. This one has 6. So if you put 2 in one and 2 in the other, 6 would be the most you could draw that were equivalent. So that is the one that has the most disorder in it. And that is how the definition plays out. Now, when we're talking about a few particles and a couple different choices of where they can be, it's not that complicated. It's not, you know, it's not trivial, but it's not that complicated. But imagine a container that has millions and billions and quadrillions, a mole even, of molecules in this thing, and you're trying to talk about entropy. It could get pretty complicated pretty rapidly. So here's what I want you to think about and hold on to when you're thinking about entropy. I want you to associate it with disorder, okay? Our brains are really quick at looking at two systems and saying this one has more disorder than that one. Just think about a dorm room, okay? You can look at one dorm room and you can look at another dorm room. Susie over here has got all her books on the bookshelf. Her pencils are in a little pencil container. Her bed is made and her clothes are all hung up. And then you go over here to Joe's room. Okay, I don't know if Joe's worse off, but this Joe is, okay? Not all Joes, but this Joe, you go into his room and his clothes are everywhere. He's got some empty Coke cans laying around and he has papers everywhere. Now, when you look at that, can you easily judge which one is more disordered? Sure, we're experts at that. And entropy can be thought of in terms of that disorder, okay? The more increase in disorder, the more entropy something has. And we'll hang on to that definition and think about it in that way more than they will think about energy equivalent microstates, because it is easy to judge, and that association is really, really powerful at judging quickly what state is more disordered than another state. Okay, so the larger the disorder, the greater the value of entropy, S. That's how we'll think about it. And we will always talk about disorder. We won't talk about order. Now, it's true that the more disordered something is, the less ordered it is. So we could talk about order, but I'm going to keep my language always in terms of disorder, because as disorder increases, entropy increases. And things have a lot of disorder, okay? There's a lot of ways that you can arrange things, a lot of disorder. All right. So let's think of another situation, not a bedroom, but a deck of playing cards. Did you know that when you buy a brand new deck of playing cards, they're all aligned according to suit and by their numbers going in sequential order? That's how you buy them. You break the seal, you crack it open, and you shuffle that deck. Now, as soon as you shuffle a deck, is it easy for you to determine whether it was the fresh deck or the shuffled deck that has more disorder? You could shuffle your entire lifetime and you're not going to get it back in that same. Its probability is astronomical that they would all land back in that same order that they were in before. So a shuffled deck, easy to say, it is more disordered. You plant a garden, you've weeded it, you've watching those little seedlings grow, and you go off on vacation and come back a week later, it's easy for you to know that the disorder has increased in that garden as the weeds have grown. Okay? So, something that you need to know about entropy is this. That's not true for internal energy, that delta E and that delta H, that enthalpy. Those things we can never say, this is how much energy something has, or this is how much enthalpy something has. We can talk about changes. We can know how much it increased and how much it decreased by monitoring what's happening around it. But we can't say this is how much it has. It's way too complicated and way too many things involved. There's electrons, there's a movement of the molecules, and there's a nuclear energy inside, and you cannot know precisely how much energy or enthalpy something has. This is not true with entropy, the S one, okay? With entropy, it is possible to have, this is how much it has. It is easy to make a judgment about the value of S, and you don't always have to talk about it in terms of change in like we have to for the other two guys. So that's just something out there for you to hold on to and think about, the fact that you can know how much entropy something has, but you can't know how much enthalpy. Now, I just said two words that sound alike to you. Entropy, yeah, you can know how much entropy something has. Enthalpy, no, you cannot know how much enthalpy something has. Okay, so let's look at these three flasks here, okay? Now what I have in these three flasks is the one on the left is a solid, the one in the middle is a liquid, the one on the right is a gas. And we're seeing what's occurring on the molecular level. We know that in a solid the molecules are touching each other, they're not moving past each other. In a liquid they're a little further apart. And what we can't see in this picture is that they are still moving, okay? So over here we see them, you know, looking like they're moving, right? These guys are still moving. They're just not moving as rapidly around in here, and they're moving past each other a little bit. All right, so what is standard? When we put this word standard in front of it, it's nothing more than entropy if you're measuring it at 1 atmosphere. So that's the external pressure pushing down on it. Now it doesn't necessarily have to be at 25 degrees Celsius, but when we look them up in tables, they are reported at 25 degrees Celsius. When it's standard entropy, we will put a little guy up there. Looks like he's got a dot inside. There we go. A little guy up there. That tells me it's in standard state conditions. Okay? Now, if you take a substance and it changes states, it's going to change its value of entropy. So let's think about what's going on in this image. Okay? As you go from a solid to a liquid, it's going to increase the entropy. As it goes from a liquid to a gas, it's going to increase its entropy. So let's get an image in our mind of something, a situation that you would be familiar with that you could hold on to with this. Let's imagine that the solid, you've got some classrooms where you're sitting in the room and everybody is sitting in their little chairs and nobody is moving out of their chairs during the lecture. They're all in rapt attention, I'm sure, with what's going on in the front of the room, and everybody is sitting next to its neighbor. That's kind of like the solid state. You're not moving past each other at all. Now, if I am in that classroom and I see that everybody is sitting in rows and I'm sitting back and judging the chaos, the disorder in there, I am seeing disorder. You are not perfectly ordered. I've got people who are rummaging through their backpack over here. We've got somebody who's diligently taking notes here. We've got somebody who's nodding off over here and jerking themselves awake, whatever. We've got a lot of motion. So if I look at the whole, I'm seeing movement. Now in a solid state, the molecules are vibrating still. So there is that little motion you've got going on there. So there is some disorder associated with the solid state. But in the classroom, there's a point where I might say, okay, everybody, I don't like where you're sitting, and I want you to get up and I want you to move, and I'm telling you what my parameters are for you to move. And I stand back and I watch as you all get up and move to a different seat. While you're moving past each other and moving around in that room, you are like in the liquid state. You're still attracted to each other. You're still associated with each other because you're in the same classroom. You're just sliding past each other as you make your way to a new place. That's like the liquid state. Now, if you were to stand in the front of the room with me and watch that happen, it is obvious that there is much more disorder in that room as people are moving about around the room. And that would be like the liquid state. So there's an increase in the disorder. I want to say that class gets over at 11:50 and now everybody, whew, they pull far apart from each other, and some may be going over to get dinner, and some may be heading to another class, and some may be going back to their dorm room, and they're going all over campus. And if I could just sit back and watch only my students and watch what they were doing, man, the disorder amongst those people would have increased drastically. That's kind of the gas state, where you're no longer attracted to each other in any way, shape, or form, and you're moving about independent of each other, and that would be the gas state. So thinking about it in terms of disorder, you can see that it would increase as you move across the screen. So we have the solid is less than the liquid, which is less than the gas. Now very often I will report this with 2 of these symbols, because when you go into the gas state, this really increases in its entropy. So a lot of times we'll put 2 greater than or less than, depending on which way you're looking at it, symbols between the liquid and the gas state. So entropy is a state function, okay? It's with a capital S, and anytime you have a state function, you can determine the change of that thing by taking the final minus the initial. So you think back to this image here, okay? You think about this image and you answer this question. If you're going to evaporate water, think about the states it's changing between as you evaporate it. Will it have a positive change or will it have a negative change as it goes through this process? Well, I hope you said it has a positive change. If we look back at our picture, it's going this way, right? It's a big number minus a smaller number. Okay, big minus small is a positive value. Anytime something gets bigger, it is a positive change. So we're going to look at some other examples of processes that give you a positive delta S. Okay? We're going to continue thinking about this image for a little bit. So everything that I write up on the screen there are going to be things that have a positive change. And I'm going to put another one of these symbols right there. Okay, the first one. If you go from a solid to a liquid, what is that called? Melting. It can also be called fusion. Okay? If you're going to the right, it's going to have a positive, greater than 0, delta S. Okay? If we go from the liquid to the gas, which is vaporization, okay, we can do it rapidly and it'd be boiling. As you go from the liquid to the gas, you are increasing your entropy, so that would be a positive change. As you move to the right, it is a positive change. Now for the next one, let's look at another picture. I have a solute that I'm putting into a solvent. Now I'm going to let you know something, that for my image here, they must both be molecular. If one of them is ionic and one of them is molecular, all bets are off in terms of this statement. But if they're both molecular compounds, then as we look at the solute and the solvent, they are organized according to their like kind. Okay? And then they're turning into a solution where they're haphazardly mixed together. So if you're thinking about entropy as disorder, can you tell that one is more disordered than the other? As you make that solution, as you mix those things together, you are going to have a positive entropy change. It is becoming more disordered. So anytime you think of positive entropy change, you're thinking becoming more disordered. Okay? The truth of the matter is that you have an increase in the number of energetically equivalent microstates. All right, there's another one in here that I don't have a good picture for, and I will here in a minute. Anytime you increase the temperature, you are increasing the disorder. So we could think about, go back to our classroom and think about your all's molecules going past each other as I'm making you in the liquid state. I said, okay, I want you all to move around the room and find you a new seat, and as you're moving past each other, you're the liquid state. And then I say, hurry, 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 and you all speed up twice as fast. And you start bumping into each other and colliding, and raising that temperature is raising the kinetic energy, which is raising the velocity of the molecules. I mean, if you think about it in terms of the classroom and people running around, when you raise the temperature, you see more disorder. So an increase in temperature is an increase in disorder. Now, if we think about it in terms of energetically equivalent microstates, then this image is helpful for us. There are two temperatures being represented on the screen here. Temperature 2 is the higher temperature. Temperature 1 is the lower temperature. At temperature 1, the number of choices of where the molecules could have energy is much, much greater than the number of choices of energy a lower temperature can have. Okay? So when we're talking about we see a very different distribution. In both cases, you have low energy, low energy. Here we got some mid-range energy. But in this case, there's a whole lot more choices of the energies they can have. So you're going to have more possibilities of energy equivalent microstates as these guys shuffle around their energies in order to give you that temperature. But if you think about it in terms of chaos and disorder, and the speed that they're traveling is going to always increase the entropy. So T goes up, entropy goes up right along with it. So here is kind of a summary of the temperature and the state arguments that you've got in your notes. You take a solid, you start warming it up. As it warms up, the entropy increases because as temperature goes up, entropy goes up. Then you melt it. As you melt it, it takes a big jump. It doesn't change temperature while it does that melting, but takes it on a big jump in its entropy as it climbs up. And then once you melt it, the temperature can rise again. As the temperature is rising, the entropy goes up. Then it hits the boiling point and it starts boiling. We have a very rapid increase in the entropy as it turns into a gas. Temperature doesn't change while it's boiling. It stays at a certain temperature while it boils. Once it's in the gas phase, then the temperature can rise again. So those connections are things that you have got to hang on to in order to answer a lot of questions that we are going to see throughout the thermodynamic chapter. Okay, so we define entropy, this S thing, okay? What we have got to do in our next lesson is, once we know entropy, go back to what is the purpose of thermodynamics? It's to predict whether or not a process is going to be spontaneous. So we're going to work more with entropy and that concept in our next lesson.